Assalamualaikum and hello. Let's continue with the next part 3, Introduction to Organic Chemistry, where we are going to focus about reaction in organic compounds. For your information, chemical bonds such as covalent bond can be splitted, and we call that process as bond cleavage, or another term is bond breaking. There are two types of bond breaking for covalent bonds. The first one is homolytic cleavage and the second one is heterolytic cleavage. I made a table for you so that you can compare a few characteristics between these two cleavage. Let's focus with the first characteristic, the definition itself and how homolytic cleavage occurs. It only occurs in non-polar bond involving two atoms of similar electronegativity. However, for heterolytic cleavage, it happens in polar bond involving two atoms of different electronegativity. The second one, we are going to take a look at the description of each bond cleavage. For homolytic cleavage, a single bond breaks symmetrically into two equal parts, leaving each atom with one unpaired electrons. However, for heterolytic cleavage, a single bond breaks unsymmetrically and both bonding pair electrons are being transferred to the more electronegative atom. This is where you are going to take note at which atom in polar bond has partial positive charge and which one got partial negative charge. And once the single bond breaks either symmetrically or unsymmetrically, the product will form, and free radical is a product for homolytic cleavage, while positive or negative ion are the product for heterolytic cleavage. And then I got the example how you want to write the equation for homolytic cleavage. The most important things that you have to indicate is the presence of ultraviolet lights. This is UV. Once the single bond breaks symmetrically and transferred one electron to Cl at the left and one electron at Cl at the right, you will get two Cl radical. So another way that you can write it down as Cl dot plus Cl dot. So this is another way that you can write as the products form, instead of you write it as 2Cl radical. And the next one, for heterolytic cleavage, we know that there will be partially positive at CH3 and partially negative at Cl atom. So once you see there is a significant difference between electronegativity of carbon and chlorine, and of course two electrons will be transferred to the most electronegative atom, in this case is chlorine, and that's why you will get positive ion CH3 plus and negative ion Cl minus for your products. Last one, when you want to draw the arrow for homolytic cleavage, you have to know that we are going to transfer one electron. So how you want to illustrate that one? We are going to draw half-headed arrow, either this one or this one. So which one that you prefer? This is how you draw half-headed arrow. And then for heterolytic cleavage, you know that we transfer two electrons. It means that the arrow must be full-headed. So you can draw it just like the normal form that you draw the arrow. So that's how you want to see the comparison between two types of bond cleavage. In this case are homolytic cleavage and heterolytic cleavage. Now I'm going to focus a bit more about the process, how you want to explain the homolytic cleavage. Homolytic cleavage is endothermic process because energy is being absorbed to break the covalent bonds, and this energy is coming from sunlight or high temperature. But when we want to write the equation, you have to put UV under the arrow. So as you see from here, you split the covalent bond symmetrically for each Cl atoms. You will get two chlorine radicals. And you have to understand these free radical chlorine are reaction intermediates. So it's very reactive and very unstable. So it cannot stay as it is in that radical form. That's why it will try to react with another compounds or another radicals. So please understand that it's very reactive and very unstable. For example, I have methane undergoes homolytic cleavage with UV as your special condition. What will happen? The bond between carbon and hydrogen will be splitted equally, and CH3 radical, or another name we call it as methyl radical, is one of the products, and the next one is hydrogen radical. This is another examples for homolytic cleavage that can happen in methane. So I hope you are clear with these examples. Let's continue with the stability of free radical. For example, I have methyl radical where my carbon atom got radical which connected to 3 hydrogen atoms. So this is methyl radical. Once I change one of the hydrogen with another alkyl group, in this case is CH3, so I got this carbon with 2 hydrogens and 1 alkyl group. So this is what we call as primary free radical. And if I change one of the hydrogen from here into another alkyl group, for example, I change it with benzene ring, I only got 1 hydrogen left, and this form is what we call as secondary free radical. And last one, if I change all hydrogens around this carbon free radical, so I got 3 alkyl groups around them, this will be tertiary free radical. So if you want to understand about stability of free radical, it depends on the number of alkyl group exists in free radical species. For example, this one we got no alkyl group, but here you got 3 alkyl groups. The more alkyl group exists in your free radical species, the more stable that species is. So in this case, tertiary free radical is the most stable one. This is because alkyl groups are electron donating group. Another term we call as EDG. So what is the purpose of EDG? EDG helps to disperse the charge on the free radical. What does it mean by disperse? It means that EDG or alkyl group in this case stabilize the reactive free radical, because we know that free radical is very unstable and very reactive. In order for it to achieve stability, we are going to add EDG in its form. So that's why the higher number of EDG in free radicals, the free radical will be more stable than another. Now, let's continue with heterolytic cleavage. Heterolytic cleavage only involves 2 atoms with different electronegativity. For example, I have CH3 bonded to Cl, so the covalent bond here will be splitted unsymmetrically towards most electronegative atom, carbon and chlorine atom. Carbon is partial positive, chlorine atom is partial negative. So of course, all electrons from this covalent bond will be transferred to chlorine atoms, which making your products contain CH3 plus and Cl minus. CH3 plus is what we call as cation or electrophile, or the special one, carbocation, which is carbon with positive charge. And Cl minus is what we call as anion or nucleophile or carbanion. So this is another term that you have to memorize because you will see it very often in this course. Now we are going to take a look at the stability of carbocation. So stability of carbocation depends on how many alkyl groups attached to carbocation. It's just the same case with free radical. The more alkyl group, the more stable the carbocation. For example, you got methyl carbocation here, where CH3 with positive charge, and the number of alkyl groups keep increasing from primary carbocation to tertiary carbocation, and the most stable one is tertiary carbocation because the presence of alkyl group is the most higher in this form compared to methyl carbocation, and alkyl groups acts as EDG that helps to stabilize the charge on carbocation. So what can we conclude from here? The presence of alkyl group in your structure, whether free radical or carbocation, is very important. So how you want to know whether that form is alkyl group, how you want to determine the structure of alkyl group? I give you a few examples. You know that alkene, one example of alkene is methane, with its chemical formula is CH4. So when methane becomes alkyl group, the name will be changed to methyl, and the chemical formula will be less one hydrogen, and it will bonded to something else. So this dash means bonded to something, and the chemical formula will be CH3. Same case with ethane, and what you're gonna do once ethane becomes alkyl group, it means that the name will be changed to ethyl, and the structure will be attached to something else in form of CH2CH3. This is how I make it very simple for you to understand. As you see from here, methyl carbocation, methyl carbanion, and methyl radical. I'm not focusing on methyl carbanion too much because this one is out of the syllabus, but at least I want you to see that methyl carbanion can also exist as primary, secondary, and tertiary. Same case with methyl carbocation and methyl radical. And these are the special terms that you have to understand because you will see these terms a lot during this semester. Free radical, positive ion, negative ion, carbocation, carbanion, and of course, last but not least, electrophile and nucleophile. We are going to focus a lot more by using these terms in the next video. So that's all for this one. I'll see you in the next video. Thanks for watching. Bye.